All right, pre-cal pumpkins. We are still dealing with 4.1. This is video 3. I'm just going to talk to you a little bit about exponential functions. We do use exponential functions for several different things, and we will do some of these application problems in the coming videos. So we use exponential functions. Some of the things we use them for are compound interest, continuously compounded interest. We use them to show bacterial growth and decay, population growth and decay, radioactive decay, things like that. So I think I said bacterial decay. I didn't mean that. Bacterial growth and population growth and decay and radioactive decay. That's what I meant to say. All right. So one of the things that comes into play in some of these formulas for these applications is this idea of a Euler number. So it is an irrational number, so it's kind of like pi, all right, and we use a letter to represent it, just like we use pi for 3.14 extending out forever. Well, the Euler number is a similar number. It's got a value of 2.718, roughly. But since it's irrational, it goes on forever. All right, so we use it, of course, in the applications that I just listed above this information. So before we get started, let's look at a natural exponential function defined this way. It looks just like this. F of x equals e to the x, and obviously we are in a base of e. Well, since I know that the Euler number is 2.718, that means that e, of course, is going to be greater than 1. It's 2.718. All right, so if we're going to graph it, I have to think of e now as a base greater than 1. That means that I have a situation where it increases to the right, because remember, if you remember from the very first video, I told you that. All right, so there's some other stuff going on here, though. If you'll notice, there's a negative x. The negative's not in front of the e, it is in front of the x. That means we reflect over the y-axis. If it's in front of e, it's over the x-axis. And the positive 2 means that we are moving up 2. So we're taking this parent function and we're shifting it around. So the parent, since the Euler number is bigger than 1, would look something like this, but it's going to reflect over the y-axis. So it's going to do this. Okay, and it's going to move up too, so it's going to move right up here. So let me erase this other stuff. Okay, that means that my asymptote is also going to shift up too. So y equals 2, and it's going to look something like that. So make sure you label that value. Okay, so I'm just showing you how we would graph this. The rules for graphing don't change just because we're dealing with the Euler number. E has a value of greater than 1, 2.718. All right, so how are we going to use this in finding some of these application problems? Well, we use the E in the formula. Let me show you what I mean. Compound interest formula looks like this. Don't freak out. You're going to be using a calculator to find all these values. Okay, so what do all these letters mean? Well, the P is the principal. That's the value you start with. The R represents the rate. The N represents the number of times per year that the interest gets calculated. And T is equal to, dang it, T is the time in years. Okay, so all of your letters are accounted for. Continuous compound interest formula looks a little different. It requires the use of the Euler number. So again, the P here is the principal. The E, of course, is the Euler number. and it's a value, so we don't really define it as E. We know that it's 2.718. Okay, 2.718, did I say that right? Yes, I did. Okay. R is the rate, T is the time in years. All right, so what is this going to look like in terms of a problem? Well, we have Katie here. She invests $300 in an account with 6% interest. That's your rate, by the way. This is your principal. Making no other deposits or withdrawals. What will Katie's account balance be after 20 years? That is T. If the interest is compounded semi-annually. All right, so I want you to notice that it is compounded semi-annually or monthly. I want you to look down at number 6. Notice I tell you it's compounded continuously. If I don't use the word continuously, I'm dealing with this formula right here. Okay, so semi-annually, that means twice a year. So 2 times a year. All right, what is this going to look like? Well, we're going to use this formula. So the principal is 300 times 1 plus R over N. R is 6%, so 0.06 divided by N, which is 2 times a year, to the N times T. So N times T, so 20 years. Okay, I'm told that it's 20 years. So basically, all I have to do is type this into a calculator. And I come up with 978.61. The only thing you have to be careful about in your calculator, if you've got a graphing calculator, make sure you're using your parentheses correctly. And of course, make sure you're following PEMDAS. All right. If it's monthly, there are 12 months in a year. So this is going to be 12 times a year. Okay, so this is the N. I'm still dealing with the same information otherwise, though. The principal is 300. It's 1 plus 0.06 over 12 this time instead of 2. And then to the exponent 12 times 20, because I'm still dealing with 20 years. So what would that be? You'd get 993.06. Magic. All right, the next one we're going to do is number 6. Suppose Katie finds an account that will allow her to invest her $300 at 6% interest rate compounded continuously. That means we are going to use this formula right here. If there are no other deposits or withdrawals, what will Katie's account balance be after 20 years? Okay, so again, my principal is 300 times E to the 0.06 times 20. In your calculator, there should be an E button. So obviously, I don't have my calculator pulled up on my iPad, so I can't show it to you. But I will show you in class when we're together if you don't know what that is. All right, so that's how you use the Euler number and exponential functions to find interest compounded and compounded continuously.